Good morning, everyone. I am delighted to welcome you all today. Thank you for joining me for this presentation on oscillation. Today, we will explore the fascinating concept of simple harmonic motion, or SHM. I'm Farzeen Samir Sheikh, and I am excited to guide you through this topic. This seminar is brought to you by the School of Nanoscience and Biotechnology. We will cover the fundamentals of oscillations, their applications, and some interesting insights. So, let's get started and dive into the world of oscillations. So, what exactly is oscillation? Well, oscillation is really just a repetitive back-and-forth movement of a system around a central point, or what we call an equilibrium position. Think of it as something swinging back and forth or vibrating regularly. For example, a swinging pendulum, a vibrating guitar string, or even a child on a swing. These are all classic examples of oscillations. Now, a key point to understand here is that oscillations happen because of something called a restoring force. This force always acts to bring the system back to its original position after it has moved away. It's this push and pull that keeps the motion going in a regular pattern. Recognizing this restoring force is fundamental because it explains why oscillations are repetitive and predictable. Connecting this to our overall theme, understanding oscillations helps us grasp the underlying principles behind many physical systems, from simple playground swings to complex mechanical and electronic devices. It's all about how systems naturally tend to return to their equilibrium, creating that rhythmic motion we observe. Now, let's explore the different types of oscillation. First up is free oscillation. This occurs when there's no external force acting on the system, like a pendulum swinging once you've given it a push. It continues to swing back and forth on its own, gradually losing energy over time due to air resistance and friction. Next, we have damped oscillation. In this case, the system loses energy over time because of these resistive forces, so the amplitude of the oscillation decreases gradually. Think of a swinging door that slows down and eventually comes to a stop. That's damping in action. Moving on, forced oscillation happens when an external force continuously acts on the system, keeping it oscillating. Imagine pushing a swing at just the right times to keep it moving. You're applying a periodic force to sustain the motion. And finally, resonance. This is a fascinating phenomenon where the amplitude of oscillation suddenly increases dramatically when the frequency of the external force matches the system's natural frequency. It's like pushing someone on a swing at just the right moments, causing them to go higher and higher. Understanding these different types of oscillation helps us grasp how systems behave under various conditions, which ties back to the overall theme of how vibrations and periodic motions influence physical systems. So, what exactly is simple harmonic motion, or SHM? Well, it's a specific type of oscillation, and understanding this helps us grasp many physical phenomena around us. Essentially, SHM occurs when the restoring force acting on an object is directly proportional to its displacement from an equilibrium position. That means, the further you displace the object, the stronger the force pulling it back. An important point here is that this restoring force always acts in the opposite direction to the displacement. So, if you push an object to one side, the force pushes it back toward the center, trying to restore equilibrium. Now, mathematically, this relationship is captured by the formula F equals minus K times X here. F is the restoring force, K is a constant specific to the system's characteristics, and is the displacement from equilibrium. The negative sign is crucial because it indicates that the force opposes the displacement. It's always acting to bring the object back to its starting point. Connecting this to our overall theme, understanding SHM is fundamental because it describes many oscillatory systems, from pendulums to springs, and even molecular vibrations. Recognizing the proportionality and the opposite nature of the restoring force helps us analyze and predict the behavior of these systems effectively. Let's take a closer look at the equations of simple harmonic motion. These equations are fundamental because they mathematically describe how an object moves when it oscillates back and forth in simple harmonic motion. The key idea is that the motion is sinusoidal, meaning it follows a sine or cosine pattern. First, we have the displacement equation, which shows how the position of the object changes over time. It's typically written as x equals a times cosine of omega t plus a phase constant phi. Here, A is the amplitude, which is the maximum displacement from equilibrium. Omega is the angular frequency, indicating how quickly the oscillation occurs. And phi is the phase constant, accounting for the initial position at time 0. Next, there's the velocity equation, which is derived by differentiating the displacement with respect to time. It tells us how fast the object is moving at any given point, and it's proportional to the sine of omega t plus phi, scaled by a and omega. This means that velocity reaches its maximum when displacement is 0, and vice versa. Then, there's the acceleration equation, which comes from differentiating the velocity again. It shows that acceleration is proportional to the negative of displacement, reinforcing that the restoring force always acts toward equilibrium. Mathematically, it's expressed as negative a times omega squared times cosine of omega t plus phi. These equations are interconnected and form the backbone of understanding simple harmonic motion. They help us predict the position, velocity, and acceleration at any moment, which is crucial for analyzing oscillatory systems in physics. And as we see, they beautifully illustrate how the motion is periodic and predictable. Let's take a closer look at the characteristics of SHM. First, simple harmonic motion is characterized by its periodic nature, meaning it repeats itself at regular intervals. This regularity is what makes it predictable and easy to analyze. Next, the motion is sinusoidal, which means the displacement, velocity, and acceleration follow a sine or cosine pattern over time. This smooth, wave-like behavior is fundamental to understanding how systems oscillate in SHM. Another key point is that the restoring force in SHM is directly proportional to the displacement, but acts in the opposite direction. This proportionality is what keeps the motion oscillating back and forth around an equilibrium point. Additionally, the amplitude of SHM, that is, the maximum displacement from equilibrium, remains constant in ideal conditions, meaning there's no energy lost to friction or resistance. The period and frequency of SHM are determined by the system's physical properties, like mass and stiffness, which ties back to the overall theme of how physical parameters govern oscillatory behavior. Understanding these characteristics helps us not only describe SHM accurately, but also see how it applies to real-world systems, from pendulums to vibrating molecules. Let's take a closer look at energy in simple harmonic motion. When an object oscillates, it possesses both kinetic energy and potential energy at different points in its motion. At the maximum displacement, or amplitude, the energy is entirely potential because the speed is 0. Conversely, at the equilibrium position, the energy is purely kinetic since the object is moving fastest and the potential energy is 0. Throughout the motion, energy continuously transforms between these two forms, but the total energy remains constant in an ideal, frictionless system. This interplay between kinetic and potential energy is fundamental to understanding how oscillations behave and how energy is conserved in simple harmonic motion. Recognizing these energy changes helps us better grasp the dynamics of oscillatory systems and their applications. Now, let's look at some real-life examples of simple harmonic motion in everyday systems. First up is the spring mass system, which is a classic example. When you compress or stretch a spring, it oscillates back and forth in a smooth, repetitive motion, illustrating the principles of SHM very clearly. Next, consider the pendulum, but with a small angle approximation. When the swings are small, the pendulum's motion is nearly sinusoidal, making it a perfect real-world example of SHM. It's fascinating how such a simple setup can demonstrate complex oscillatory behavior. Moving on to more familiar sounds, think about a tuning fork. When struck, it vibrates at a specific frequency, producing a pure tone. These vibrations are a perfect example of SHM in the realm of acoustics. Similarly, a vibrating ruler also demonstrates harmonic motion. When you flick the end of a ruler that's resting on your finger, it vibrates and produces sound, again showing oscillations that are predictable and periodic. Finally, in the realm of electronics, LC circuits, comprising an inductor and a capacitor, exhibit oscillations of electric energy. These circuits oscillate between magnetic and electric fields, perfectly illustrating electrical SHM. All these examples highlight how SHM appears in various forms across different fields, reinforcing the idea that this type of motion is fundamental to both natural phenomena and engineered systems. Let's take a closer look at the differences between oscillation and simple harmonic motion. While both involve repetitive movement, there are some key distinctions to keep in mind. Oscillation is a broad term that refers to any periodic back-and-forth movement, which can be irregular or complex. In contrast, simple harmonic motion, or SHM, is a specific type of oscillation where the restoring force is directly proportional to the displacement and acts in the opposite direction. This results in a smooth, sinusoidal motion that's predictable and consistent. Understanding this difference helps us see how various systems behave, whether they follow a predictable path like in SHM or exhibit more complex oscillations. Recognizing these nuances is fundamental to grasping the broader concepts of wave motion and energy transfer we've been discussing throughout this presentation. Oscillation truly is everywhere, from the way machines operate to the tiniest molecules in nature. It's a fundamental concept that helps us understand many phenomena around us. When we talk about simple harmonic motion, or SHM, we're really exploring how vibrations and waves behave, which is crucial in so many fields. SHM isn't just a theoretical idea. It forms the backbone of many technologies we rely on daily. For example, clocks use precise oscillations to keep accurate time, sensors detect vibrations to monitor environments, and communication devices transmit signals through wave patterns. So, understanding oscillation and SHM gives us insight into how these technologies work and how they continue to evolve. It's a foundational concept that connects everything in our modern world. Thank you for your attention, and I hope this overview has shown just how central oscillations are to both science and technology.